All right, let's get started. First, we need to install Python and import TensorFlow. So we'll do that with the command. Then we import TensorFlow as. We also need to bring in some layers from TensorFlow's Keras module, so let's import those as well. Additionally, we'll import NumPy as and Matplotlib for plotting as. To ensure our results are reproducible, we set a random seed. We do that with. Now let's move on to defining the generator model. We'll create a function called. Within this function, we'll initialize a sequential model using TensorFlow's Keras module. First, we add a dense layer with 128 units and ReLU activation. This layer will take an input shape of 100. Next, we add another dense layer with 784 units and sigmoid activation. This corresponds to the 28 by 28 pixel images of the MNIST dataset. Finally, we reshape the output to match the 28 by 28 format, and that's our generator model. And next, we define the discriminator model. We create a function called. Inside this function, we again initialize a sequential model with TensorFlow's Keras. We begin by adding a flatten layer to convert the 28 by 28 input images into a one-dimensional array. After that, we add a dense layer with 128 units and ReLU activation. Finally, we add another dense layer with 1 unit and sigmoid activation. This will output a single value, indicating whether the input image is real or fake, and that's our discriminator model. Now that we have both our generator and discriminator models, it's time to compile them. We start by calling the function to create our generator model. Then we call the function to create our discriminator model. For the discriminator, we compile it using the Adam optimizer, binary cross-entropy loss, and we also include accuracy as a metric. And that's how we compile our models. All right, let's define the GAN model. First, we have the discriminator, which we set to not be trainable at this stage. We then create the GAN input layer, specifying a shape of 100. This input is fed into the generator to produce a generated image. The generated image is then passed to the discriminator to get the GAN output. Finally, we compile the GAN model using the Adam optimizer and binary cross-entropy loss. Now let's load and pre-process the dataset, specifically the MNIST dataset. We start by loading the data, which gives us the training and testing sets. We normalize the training data to a range between 0 and 1. Lastly, we expand the dimensions of the training data to ensure it matches the input shape expected by our model. Next, we move on to training the GAN. We define a function called train_GAN, which takes epochs and batch size as parameters. For each epoch, we loop through the dataset in batches. For each batch, we generate random noise and use it to create fake images. We also get a random set of real images from the training data. These real and fake images are then concatenated together. We create labels for the real and fake images, adding a bit of noise to make the training more robust. We then set the discriminator to be trainable and train it on the combined images and labels. After that, we generate new noise and set the labels to ones, as the generator wants the discriminator to think these images are real. We set the discriminator to not be trainable and train the GAN on this noise and these labels. This process is repeated for 10 epochs, and after each epoch, we print out the discriminator and generator losses. Finally, let's generate and display some images. We define a function called generate_and_display_images, which takes the number of images to generate as a parameter. We generate random noise and use the generator to create images from this noise. We then set up a plot to display the generated images in a grid. For each image, we display it in grayscale and remove the axis for a cleaner look. After training, we call this function to generate and display the images.